This lesson is on exponential functions. If you could write your title up at the top of your paper, exponential functions. We're not actually going to do this opener as an opener. We're just going to do it within our mini lesson. And what we're addressing today is the difference between exponential functions and linear functions. You've worked with linear functions for 2 years now. Exponential functions are functions that look a little bit different. Their pattern of their slope is a little bit different. They look a little different when we graph them. And that's what we're going to start to explore in this unit. So yesterday, what you looked at was a paper folding task. And in that paper folding task, you came up with 2 different equations. This first equation here, we saw a curve that increased, and it looks like we had a multiplication of 2 pattern. That function is called exponential growth. So on your paper, go ahead and write the circled function. And then next to it, you can write exponential growth. Because as our number of folds increased, the number of sections increased as well. That's considered growth. On the other side of the paper folding task, you were asked to find the area of each section as you folded it, and you would have gotten a curve that looks like this, that's decreasing. You also created this equation for that, and you notice that every time you folded the paper, the area was cut in half. And this type of exponential equation is called exponential decay. And when we talk about decay, think of that as a decrease. So we've got exponential growth, exponential decay. You might be able to start figuring out something like a way to tell which ones are always growth and which ones are always decay, and it has to do with this number right here. So to define what these 2 equations would look like in any sense, we've got this form of exponentials right here. Go ahead and write this down in your notebook, and off to the side write that this is called standard form. This is a standard form of an exponential. And you'll notice I've got 3 arrows off each piece because we're going to describe what those pieces are. Our A value, that stands for our initial value. And the initial value is like the y-intercept of a function, what we start with in a problem, our initial value. Our A value is being multiplied by B, and B stands for our base, but your base is also your pattern that you notice. So if we were to look at the example yesterday with the paper folding, when we were folding that paper and looking at how many sections we got, we noticed that there was a pattern of the sections of paper were being multiplied by 2 every time. That's why our base in this equation here was 2. Our X represents our inputs, or our domain, our independent variable. And the f of x, that represents our outputs. So these 2 didn't change from our linear functions, inputs and outputs. However, the a and the b represent just a little bit different items. So again, this is the standard form of an exponential. Make sure you've got all of your pieces labeled in your notebook as well, because you're going to be using this form to make some comparisons in a few minutes. So let's look at an example of exponential functions, and this is it. It says, situation 1, you have 20 liters of water on a very hot day. You realize that the volume of your water halves each hour, so that means it's getting cut in half each hour. How many liters do you have remaining at the end of 1 hour, 2 hours, 3 hours, and 10 hours? On your paper, go ahead and make this table. We've got hours is our independent variable, and liters of water is our dependent variable. And I'm going to fill in the table values they're asking for. So they want to know how much is after 1 hour, after 2 hours, 3 hours, and 10 hours. 1 hour, 2 hour, 3 hours, and 10 hours. So if we start with 20 liters of water, 20 liters of water, and 1 hour goes by, it says that our water halves each hour. We're taking half of 20. So what is 20 divided by 2? That gives us 10. So after 1 hour, we're left with 10 liters of water. Again, it said the water halves each hour. We're cutting our number in half every time, or multiplying by a half. If we were to cut 10 in half, we would get a 5. If we were to cut 5 in half again, we would get a 2.5. And essentially what this is showing is that we're multiplying by a half every single time, because it says our volume of water halves each hour. Now we have a 10. We have to figure out how much water we would have to after 10 hours. And instead of continuing the pattern of a half, a half, a half, a half, let's just make an equation to help us. So we're going to use this form right here, standard form of an exponential equation, to help us out. So our base form is f of x equals a times b to the x power. Here we'll rewrite f of x. A, as we just learned, stands for our initial value, or how much water that we started with, and we started with 20 liters. B stands for our pattern, and our pattern that we're noticing is that we're multiplying by a half every single time. Now, if you say our pattern is division of 2, you're right. However, when we write exponential functions, we are using multiplication. So we have to kind of convert the idea of dividing by 2 into a multiplication problem, which would be the same thing as multiplying by a half to the x power. Perfect. So we're trying to find after 10 hours, so we're going to substitute a 10 in for x. So we have 20 times 1/2 to the 10th power. This is definitely a problem that I would recommend putting into the calculator from here. So when we type that in, we're going to do 20 times, we're going to put in parentheses 1/2 to the 10th power in parentheses. Actually, when we write that, let me erase this. Put your 1/2 in parentheses, and then there's a little button that looks like, it's called a caret. It looks like this on your calculator. And we're going to take that to the 10th power. When we solve that problem, we're going to get a very small number. We're going to get 0.0195. We'll round it to the nearest 10,000th place. So after 10 hours of that water being cut in half over and over and over for 10 hours, we would have 0.0195 liters of water. Very, very small amount. Good. So what we created here was an exponential function, which we put here. We created an exponential function to help us figure out how many liters of water we had left after 10 hours. The reason why we knew this was exponential is because of the word halves right here. That's like multiplying by a fraction each time, cutting our value in half each time. So this represents an exponential function. Now let's compare that to a linear function, which is this scenario. Very similar, but let's look at the difference. You have 20 liters of water, but this time it is leaking out at a rate of 1/2 of a liter per hour. How many liters do you have remaining at the end of 1, 2, 3, and 10 hours? Let's look at that again. Make your table in your notebook. We're looking at a little bit different situation. I'm going to add a 0 to the top on this one. 0 hours. How many liters of water do I have? We have 20. And it says that it's leaking out at a rate of 1/2 a liter per hour. So look at the way half is written in this problem. It's coming out 1/2 a liter. We're not literally taking the liters and cutting them in half. We're just losing 1/2 of a liter each hour. So this is going to be a subtraction pattern. So we're just subtracting a half each time. So we start with 20 liters, and after an hour, I lost 1/2 a liter. So I'd be down to 19.5 liters. Another hour goes by. I lose another 1/2 liter. I would be to 19 liters. I lose another 1/2 a liter. I'd be down to 18.5. Now to figure out 10 hours, let's make an equation. We know that linear equations, when we have those addition or subtraction patterns, and if you notice here, we do have a subtraction pattern, we know that this is the form of our equation. So to make our equation, we know that m stands for our slope, and our slope is -1/2. Our B value is what we start with, which is just 20. So again, let's look at the differences between these. Here's our linear equation, negative 1/2 x plus 20. Here is our exponential equation, 20 times 1/2 x. So notice in exponential equations, you see the exponent. You know that this is our base or our pattern, and the 20 is our initial value. In our linear one, 20 is our initial value, and we're just simply multiplying a half by x rather than taking a half to the x power. Let's figure out what f of 10 is. So we're going to substitute that in. This is a very simple process that we've done many times, substituting a 10 into the equation. Negative 1/2 times 10 is negative 5 plus 20. When we add negative 5 and 20, we get 15. So after 10 hours, there are 15 liters of water in the pool. I knew this was a linear function because we're losing 1/2 liter per hour. Our quantity is literally not being cut in half. So when we look at the differences between these two, just to kind of wrap up our thoughts, our A value in our exponential functions represents our initial value. Initial value, kind of like our y-intercept. Our B value represents our pattern and our base. Our x represents inputs. In our linear equations, our m represents our slope, and that's similar to the pattern as well. Our B represents our y-intercept, and another word for y-intercept is our initial value, which is why when we made our two equations, we saw that both of them had a 20, but some differences is that our linear equation had a negative 1/2, we were losing that water. And our exponential equation, we didn't even need a negative sign because since we're multiplying 20 by 1/2, since we're multiplying by a number that's less than 1, our value, our initial value gets smaller as we go along, so we don't even need the negative sign there. What you're going to do in your work session today is you're going to be given 8 scenarios, I think it is, and 8 equations, and you're going to have to match them together. Once you match them together, you're going to take a picture of your matching cards, and you're going to submit it to Canvas. These are a class set, so don't write on them or anything like that. Take them from the substitute, and then you'll return them when you're done. But again, you're taking a picture of your results and making sure you submit that to Canvas. Look at your notes as you have these out. Look for those keywords. If I wanted to review those keywords again, this is dripping out at a rate of 1/2 liter per hour. So that rate tells me I'm subtracting out 1/2 liter each hour. Whereas this problem talks about the water being halved. We're literally cutting that water in half or multiplying it by 1/2 each time. Good luck on your card sort. I'm sure you'll do great, and have a good rest of your day.